Hello, everyone. Am I audible? Let's wait for a few minutes for more participants to come and then we'll start. If there's any interruption in between, do let me know. So one final check of everything. Am I audible? And is my slide visible to all of you? Okay, so let's get started today. Hello, I am Ayush Thakur and I will be talking about neural networks and will take a very mathematical approach toward it. So finally, hurrah, we have reached to a point where we have started talking about neural network. Okay, so something about me, I am someone who is keenly interested into deep learning and for computer vision. I am chair of IEEE EDS student branch chapter of Netaji Subhas Engineering College and won some competitions and is a human. So neural network, a mathematical model, Peekaboo. Why Peekaboo? Any idea? Is only because I do not want to get in get very technical or get very math savvy. I just want to give a quick preview of what this is, how it is motivated, and what and how something can be done with it. My whole idea will be to give you a perspective which not many of us have. My perspective about neural network is a bit different than what usually is written in many blogs or is shown in many tutorials. I truly believe that neural network is nothing much more than a mathematical tool, a tool at disposal through which we can do some sort of analysis, some sort of prediction, some sort of estimation using the data that we have. Okay, so today's agenda will be about what mathematical modeling is, how to do mathematical modeling, and I will go through one example, a quick example. Then we'll talk about intelligence. I won't give a lecture on intelligence because I guess we all are intelligent enough to understand what intelligence is. Then we'll show in the human aspect or the brain aspect of intelligence. Then we'll try to model this, and then we'll see how it is learning. And exactly there, it will be a peekaboo because further sessions will go deep into the learning aspect. Okay, so before starting, there's a disclaimer. Just stay with me because there is some biology ahead and some maths too. So, first topic, what is mathematical modeling? So, modeling is a process that uses maths to represent or to make some sort of prediction or to get some sort of insight in a real world phenomena. We look at a car moving, right? And we can observe that the car is changing some distance with time. Its velocity may be increasing or decreasing. These are the observations that we see. But what we see has to be modeled in some way. And that's where mathematical modeling comes in. Now, why we do mathematical modeling is a different question. The first answer, and a very clear answer to that, is because you see, we want to look ahead into the future. Humans always want to look ahead into the future, wants to predict stuffs way before time, and that's why we prepared a language through which we can do that, and that language is math. We have lots of tools available in mathematics through which we can model more or less everything that we observe. Yeah, we have an exception of singularity of black hole. We do not have a mathematical model to define that, and obviously on the edge of all the explorations we are short on maths, but we'll eventually make it. Another definition of what a mathematical modeling is, it's an abstraction of real world scenario to predict the behavior, dynamics, and evolution of the set scenario. Suppose you want to quantify what thrill is. Like, I give you a task to evaluate what after watching a movie, say what sort of thrill that you got from watching that movie, or you went through a ride, and I ask you to give me a value through which I can judge that this particular client or this particular customer of that ride was very thrilled. Now, when I define this word thrill, it's just subjective. It do not carry with it a number or any representation that can be computed or through which we can do any sort of comparison, because the thrill for me will be different for the thrill for you, and thus we have to model the scenario that I just presented. So, how do we do mathematical modeling? Any guess? I would like to know what all you think. Someone asked that is deep learning all about neural network or there is something beyond that? You will eventually come to know. So some of the key aspects of mathematical modeling are: we have to define the problem statement. This is first and foremost for everything. You see, either you are doing some machine learning task or you are modeling some scenario, you have to understand what the problem is, because a clear understanding of the problem will ease your life, will make the whole analysis or the selection of the tools that you require to do that analysis easier. Once you have the problem statement defined, as in I said in the previous scenario when I talked about, to say after going through a ride, tell me what's the thrill that particular customer or that client got. So you have to define what thrill is, and therein lies assumptions, because you have to assume that maybe some parameters you just cannot consider everything. Maybe in the scenario there may be a case wherein you have a heavy downpour and the ride is still going on. You cannot, as you cannot consider that into the mathematical modeling process, because that's an outlier. We make an assumption so that the whole process gets easier. We get rid of those parameters which can be constraint for us. And once we make those assumptions, we define the variables or the parameters. Because many times, like say if you want to compute momentum, and you know that the momentum depends on velocity and mass, knowing the parameters or the variables can at times give you insight of what the parameter of the output, or in this case momentum, you are looking at. So these are the three key aspects or the starting aspect of a mathematical modeling process: define the problem statement, make assumptions, and define the variables. And then once you are done with all this, you can go for the solution. And now this, the whole process is iterative, because you will go through the solution, you will come upon something, you will start making assumptions again. Maybe the whole stuff falls apart and you again have to define your problem statement. You again have to reassess what you want to answer, or what problem you want to tackle. And thus this is a go back and forth process. So let's go through an example of mathematical modeling, a very simple example.
Example is leave Earth's gravity. So I would like to know what all you think when I say to leave Earth's gravity. Obviously, you will think of a rocket leaving Earth and getting into orbit, or going to Moon or Mars. These days, this is very famous. We are all heading towards Mars. So a very simple problem wherein I want my subject, an object, to leave Earth's gravitational pull. So we start by defining the problem. So let's say what is gravity, and then say how to leave Earth's gravity. These are some of the questions that may arise while defining the problem statement. And then suppose we came about some insight that, okay, fine, if I want to leave Earth's gravity, let's have a velocity which is enough for me to overcome this gravitational pull, and that's the escape velocity. So what are the assumptions that we made, that we can make? Like, we hit the minimum escape velocity, any object with a velocity above that can leave Earth. This is an assumption. That means we have defined our problem statement to the lower bound, and we are not even bothering what the upper bound is. We have excluded factors like drag in our modeling process, because the drag is a very dynamic stuff and it will depend from object to object. Just to simplify the whole process, let's exclude math. Let's exclude drag. And then we won't bother how to achieve that velocity. Let's just compute what that velocity will be. Because that problem of how to achieve that velocity will be of someone else. Right. Right now, be in a zone where we are all mathematician and we are just bothered about computing and not engineering. And then the last step to define the parameters. Since we have gravity in question, we can look back and try to find out if there is any mathematical model for gravity. Luckily, we have, courtesy to Sir Isaac Newton. So, if there is a mathematical model to a sub problem, there must be parameters defined for that model, and in this case, the gravitational constant or g. Since we want to calculate or compute the velocity through which we can leave Earth, we must have a parameter, say VEST or Vscape. Then the object that is leaving the Earth should have a mass, say m, and then we have other parameters at the radius of the Earth and the mass of the Earth. I talked about defining the problem statement, making an assumption, and defining the parameters. And I'm not bothered about the solution. If you want to check the solution, you can use this link and check out the solution. And I'm pretty sure that every one of us know how to calculate escape velocity because we all have done this in our standard 10, 11, 12, even first and second semester of our engineering. So any questions till now? Anything that's not clear or anything that's I guess everything is not so complicated till now. I guess no one is having any query right now, so let's go ahead. So we'll talk about the most important part right now: intelligence and the whole modeling, the neural network, etc. So till now I talked about or I gave an intuition of how and why mathematical modeling. It's very important because everything that we observe is translated into a language that is widely understood and can be made understood and can be understood by a machine or can be computed using a machine is good. That will give us more power over that scenario. We can do, say, if you have a mathematical modeling of water flowing through a pipe, we can simulate that. Or if you have a mathematical modeling of how two massive objects or two celestial objects interact with each other, the model of gravity, we can simulate and look and predict some other results. So mathematical model is required to predict more results, to get more insights into an observation. Let's talk about human nervous system because this is the inspiration for neural networks. So a human nervous system is actually the relationship between the outward environment and what the stimuli we produce. Suppose you touch a hot pan. Obviously, you are getting some sort of response or some sort of impulse from that. That's the input for us, right? And something is happening in our brains, and then we are removing our hands quickly. We are responding to that heat that we are receiving through our fingers or our hand. We got some sort of thermal input, and we are responding through the flex of our hand. Something might be controlling this whole process. Something might be processing this information, the heat or the thermal information that we received. Or when we look at a cute puppy and we feel happy or we do an awe, something must be like that particular those lights that we are seeing through our eye, it's been translated into an O, right? So some processing is going on. So suppose we take the inputs, which is the outward environment, right? Environment outside a human body or any animal body. Then those inputs are received by something known as receptors. These receptors are nothing but receiver nerves, right? Nerves ending that receive those uh, input. This input can be thermal input, it can be light, it can be smell, etc. Then the signal is being processed in a central nervous system or the cortex, or you can simply say the human brain, or right. And then after that processing is done, some output is being sent to what's called as effectors, which is the executive nerves. So when we are removing our hand by because we felt the heat of that pan, some information is being executed by those nerves, and that's the output. So is the what is one unit of that of our nervous system? And that's the biological neuron, right? You all may have heard of neurons. So biological neuron is nothing, it's just it's cells. I do not specialize in biological neurons, so it would be a bit clumsy. So deal with that. None of our biologists here. So basically, a neuron is a nervous cell, which is the basic functional building element of the nervous system. Our brain, or in the brain, we have something known as cortex, and in that cortex, we have about 13 to 15 billion neurons. And all the neurons are somewhere connected to about 5,000 other neurons. So there's some sort of interconnection between those neurons. Right? So whatever I'm actually trying to say right now is I'm trying to move the move the thought towards how a biological neuron or this biological nervous system has inspired the evolution of neural network, and how neural network and how the functionalities of a biological neuron can be modeled. So these neurons are actually autonomous cells because obviously these neurons got millions and millions of years of evolution, and it has become so autonomous that a single neuron can be a specialist in transmission, processing, and in storage of information. That means it can transmit information, the signals, the input signals. It can even process that signals, and it can even give it as output, and even store them. Now, how this storing works, that's none of our concern right now. Now, these neurons are have something known as dendrites, which are responsible for taking the inputs. The main body is the is the soma, and the output is received from the axon terminal. Okay, so in a very simplistic view, we have something which is taking the input. We have something where some sort of processing is happening, and then we are getting the output. So this is what I came up with. If you are given some sort of inputs to the dendrites, something has been computed, which is the output y1, y2, y3, and y4. Any guess what is being computed inside? Okay, so someone asked that what do you mean by autonomous here? Autonomous, when I say autonomous here, is that a neuron can take any role, right? There's no one defining what that particular neuron will do. A neuron can play the role of transmitting the signal. It can also play the role of putting the process signal out. I talked about receptors and the executive nerves, right? So neuron can be the receptor, it can be the executive nerve, and it can even be in your brain and can do the processing in the cortex. So that's what I mean by autonomous. Now, with the neurons, we have something called interconnection between neurons. Obviously, because we are getting some sort of input, and one single, our brain do not have one single neuron. There are billions of neurons, and there must be some sort of connection between them. See, all these stuffs, like these are the intuitions that someone observed, right? So what we observe is actually what is being converted to a mathematical model. So there are something known as synapses, and the in this diagram you can see that dendrites can receive the input, do some sort of computation. It can just pass the output from the axon, which will be the input to some other dendrite. Okay. If you remember the picture of neural network, in that we have layers of neural networks, right? And the input of one layer is the the output of one layer is the input of another layer, and something similar is happening here, right? In fact, this way of saying is wrong, because that notion of layers is actually synapses. So synapses serve as unique interneuron interface to transfer the information. Now, this is the coolest part. So, at a very early stage, like a baby, when born like 2 months old, there are million of synapses which are just randomly wired. I don't know the term hardwired, but they are actually randomly wired, because that baby do not, or that young human being do not cannot classify between a cat and a dog, right? Or cannot respond to a hot pan. There's always someone looking for that child so that he or she do not fall victim to some minor mishap. So at that stage, at that particular stage, something is happening in that body, in the brain. So actually what is happening is that the synapses are being modified. If I say a child that do not touch this particular object in this particular scenario, like when water is boiling in a pot, if I constantly keep reminding that child that do not touch that, that's harmful for you, some sort of input is being provided to that child, and some sort of modification in the connection between the neuron is happening, and thus that child learns that touching that hand is not good for him or her, and that's what learning is in a very simplified version. So someone asked, so Ritik asked that neural networks are inspired from randomly wired neural networks. See, you can say, because eventually, like at the very early stage of human being, we have all these synapses which are randomly arranged. Right? They are hardwired. Only some connection, inter neuron connections exist, which are sufficient for some processes like beating of the heartbeat or breathing, because obviously that are being controlled by our brain. And that development period was when, I mean, the period of the development of the child during pregnancy. That's where those synapses, those connections were made. Those connections were only required for uh, survival, right? After being born, this synapse is something known as plasticity. Okay, so you may have heard this term. As we grow old, the capacity of our human brain to learn new stuff decreases. Well, now this has been turned down as a myth. What actually happens is the ability of the neuron to make new connections is very high at early stage of of, of being born, and eventually this decreases. So earlier what is happening is some learning is going on. So the summary, We have something, the input, we have neurons, we have connected neurons via synapses, we have the modification of these synapses, which is the learning process, and the output. Right. So on the basis of this summary, we'll try to model out. So let's go with the modeling of the nervous system or artificial neuron. So the first process, we have to define the problem. The problem, how I see it, is dynamic generation of dynamic output based on dynamic input. Why I wrote dynamic every time? Because obviously we are generating some sort of output given an input, right? And we do not actually know what that input will be. And we also do not know what that output will be. What we are trying to model here is that biological neuron. As I said, that biological neuron is autonomous in nature. That means that neuron can take any role. It can take a role of sending the input or the receptor. It can take the role of processing, or it can take the role of putting that process information out. That's why the whole scenario is dynamic in nature right now. So we have to keep that in mind and we have to model based on that. Right? What are the assumptions that we're making? The first assumption is that the output is depending on the variable, on the input, right? The output is a dependent variable. And it's very intuitive, obviously, because just imagine you looking at a dog and saying that it's a dog. Obviously, the fact that you're saying that it's a dog depends on what you're looking. The output is depending on a variable. Now, input is independent variable. Why? Because there can be a dog or a cat. They do not care. Any subject, any object do not care what we think looking at that particular object, right? Or after smelling something with that, what if the smell do not care what we think of the smell? Either we do, either we like it or we dislike it. So it's independent.
So let's say the inputs are x1, x2, x3, and so on, and the outputs will be y1, y2, and so on. And now you can see that I am gradually progressing toward what the modern notion of neural network is, or the artificial neural network. Now this is one of the most important slide in my presentation, the inspiration from biological neuron. Remember that this particular picture where we have some inputs being fed to the dendrite and we have some output from the axon. This is somewhat similar. We have those similar inputs which are being fed to something and we have an output. So I have mapped here. The inputs are anal is similar to this dendrites. The output is that axon. We have something called excitation level or the soma, that big blob or that big cell in that neuron is representative of this excitation level. And then we have something like W1, W2, W3, W4 or the synapse or the weights or the synapses, right? Now I will go to each of these terms one by one. I would first like to take some questions, like if you have any doubt, anything in mind that you want to clear right now. I guess there's none right now. Going ahead, look at this diagram. A neuron has a representation which is mathematical in nature, right? I would like to ask all of you a question. When I say input, Or you may have heard the term features. What does it mean? What are inputs or what are the features? Anyone? Yeah, it's a perceptron. So basically, a perceptron is the mathematical model of a biological neuron. This perceptron is what we call an artificial neural network. Now let's head over to this collab link. But before that, let me just clear out few steps right here. When I say this W1, W2, W3 and W4, these are the weights. What actually I'm talking about is the input is being transferred. All these inputs x1, x2, x3, x4, assume them to be a neuron itself, assume them to be a nerve itself, right? Because nerves are only responsible for taking the input. And this y, assume that to be a nerve as well. Okay, so one particular neuron, the x1, if it has to be connected to another neuron, there has to be some sort of synapse. There has to be some sort of interconnection, and that interconnection is being provided by W1 or the weights. Okay, so that thermal heat that we got on our hand when we touch the pan, that corresponds to the inputs. Whatever information is being passed through n number of neurons, all that connections corresponds to this weight. Some sort of activation is happening, and I will talk about that, and then we get an output. Let's first head over to this notebook. So Rishira asked was what are the axons in this diagram? Axons are the nerve endings that's responsible for giving out the output. Pooja said input as in the impulses. Yes, we can say that input are the impulses, but at the very initial stage, the inputs are what we are actually observing. Like the what our human body is interacting with the outside environment. We are consuming that information as input. The link will be tinyurl/sigmoid. tinyurl.com/sigmoid. I'm just quickly going through this notebook. What I tried to do here is I tried to represent those inputs, those outputs, and those synapses, okay, or the weights. Ignore stuff that you do not understand. Like right now, if I run this dev x, this x corresponds to that big blob wherein fz was written. So this is the activation function. This right here is the activation function. Let's take some sort of input data. This is 4 by 3 data. We have some output, and then we define the weights. Okay, so now weights is actually the connection. All these values, this 0, this 1, etc., etc., all these numbers, assume them to be neurons itself. So for the connection of this neuron to another neuron, or all these neurons being connected to another neuron, the weights is responsible for doing that. Okay, so I define the weight as the first synapse is 3 cross 4, and and this 4 cross 1 is the b- bias term. What you are asking as threshold or that x0, this is what that x0 is. And right here, calculate forward through the network. Okay, I will be passing this data through this artificial neuron and we'll try to learn something. Now, how we are learning, that is something that we will talk about in the next session. Okay, something that back propagation and optimization, we will talking about that later. Right now, my main target is to make you understand why weights and then why do we do dot product. Here you can see we have something as numpy dot dot, right? So why are we doing the dot product? You must have heard, you must have gone through the blogs or the tutorials wherein you know that we do a dot product of the weights with the input and add the bias and then we activate the whole thing, right? So why do we do dot product and why not any other mathematical tool? There are so many matrix operation that is possible. Then why dot product itself? So first let's run this. You can see that there's a decline in the loss from 0.0038 I went to 0.0021 and there's this representation, right? 9.99 e to the power 0 minus 01, which is 0.99. This is also 0.99, which is close to 1. And if you look at the output, we have 0.110. So we actually approximated those inputs, the data that we have here, the features or the impulses that we have here, or the data that is being provided by these neurons are being approximated to this output using another neuron that is connecting all these neurons together. Okay, so I asked a question, then why dot product? But before that, let's see if there's any question. So now this is a very beautiful analogy that just, I guess, hit me while I was talking to one of my friend while we were discussing why this dot product. Okay, so if you've heard of something known as autocorrelation in and in signal system, right? So in signal system we have some terms as convolution, cross correlation, and autocorrelation. Let's forget all about convolution and cross correlation. This autocorrelation is a mathematical operation which gives in the similarity between the input signal with itself. See, I can delay that input signal by some time, or I can transform that input signal. Some distortion may happen to that input signal. So what's the similarity of that input signal to itself, right? That's what autocorrelation gives. So as I said that early child in like when a child is born, the synapses are kind of randomly wired, or right. In neural networks also we when we start we initialize the weights randomly. We do not have we do not give proper number to that. We just randomize, just make a random array, right? So we start with the random weights. Now let's assume that these weights are an approximation of the input. So whatever the whole thing, the whole scenario that I have been talking about is actually to map the input to the output. Okay, and to map the input to the output, we have to have some sort of approximation of the input to the output. So in case of single neuron, say suppose that those weights are somehow approximating the input. Okay, so when the weights were initialized randomly, the autocorrelation or the dot product, because you can see f dot f, right? That's the dot product. So the dot product of the input with the weight is giving you an autocorrelation, which initially is very high, because the weight which we assume to be an approximation of the input is not those are not those same values, and thus high dissimilarity. So what we want to achieve is to reduce this dissimilarity. When we reduce this dissimilarity, the weights are actually approximating the input well, or we can say that the weights are moving towards the input, right? And this is where the learning is happening. This is an analogy from signal and system, which I brought into neural network. So any question? What do you mean by differential coding right here, Ritvik? So once we have like defined or created some sort of a mathematical model for the biological neuron, and we know that it is somewhere the artificial neuron is somewhere an approximation of the biological neuron, and the scenario is similar, that we have the source same inputs and the outputs, and some sort of activation is occurring. So now let's talk about this activation. So what activation actually is? The activation is that in biological terms, activation are the impulses, right? So actually, in human body, all the signal is being transmitted through electrical impulses. Okay, so if a neuron is generating an electrical pulse, or an electricity is passing through the neuron, a path is being created, right? When I touch the hot pan, some activation occurred on the tip of my finger, that's been transmitted through my brain all the way through neurons. A path is being created, it goes to my brain, and then the exit nerves are asking my muscle to flex, right? So when a similar path, or a path when followed, which is good for that prediction, or the outcome that is desired, that's what feed forward networking is, right? So basically, in a feed forward network, we have n number of neurons connected with each other. We have the input, which are being received by the neurons, right? And these neurons are connected via weights, which is the synapses, to those hidden layers, and then we end up getting some output, right? So in a feed forward network, what actually is happening is the input, the impulses, those electrical impulses from the fingertip to our brain and back to the nerves which are responsible for flexing the muscle. That whole process is the feed forward. In artificial neural network, or in machine learning that we deal with, in that once we give the input and we let the input pass through every layer, that network topology is called feed forward topology, right? And once we have the output, we can evaluate if that output is close to the desired output, and then there comes the learning part, and then there comes the computation of the loss, and then we are updating those weights or learning those weights back through an algorithm known as backpropagation, which we will talk about later in later sessions. Okay, so after every feed forward and every backpropagation, the weights have been updated, and thus the approximation of the input is getting better, or the autocorrelation output, the dissimilarity of the autocorrelation output is decreasing, and thus we are able to map the input to the output accurately. So what the activations are? Let me show you something. This is a simple straight line, right? Y1 equals to x1. Now suppose we add two x1 and x2s, and then we can play around with this value and see that, you see, for every changing value of either one of the neuron, every x is the neuron, every y is the output of that neuron, we can see that something is happening. But you see, for a linear polynomial or a linear straight line, complex features cannot be learned. Okay, and that's where we require activation. And activation, you may have heard of, uh, in this, in that figure there was something known as threshold, right? We can say all the values which are above that threshold as 1 and all the values below that threshold as 0. That was linear activation is. But will that linear activation be able to learn very complex features or very complex relationship between the input and the output? And thus we require different sort of activations which introduce non-linearity into our network. Let's look at this quadratic polynomial. Right, if we play around with the value of this, we can change. And let's go through a cubic polynomial. As you can see, as we increase the order, as we increase the order of the polynomial, more and more complex features can be mapped. Okay, so this is what activation is. Activation is responsible for introducing nonlinearity to the network, which will be able to capture complex features. So what are some of the famous activations that we have? Some of the famous activations are sigmoid, tanh, and ReLU. Okay, right here in this notebook, 1 upon 1 plus e to the power minus x is what is known as a sigmoid function. Okay, a sigmoid function is basically a function which range from 0 to 1. So every input or the weighted sum of the dot product of the input with the weights, when we pass to that activation, we get some sort of firing or some sort of similarity between the electricity that is being generated in the neurons. Something similar is happening in the artificial neural network. Okay, now we have other activations like the tanh or the ReLU, and we will be talking about all this later because these are something which are really complex, are not very complex to understand, but a separate session on that is a really good idea. So now I am up for questions. So Aritra asks, if an input which can be through after with the impulse is huge and NN learns that and the weight is too big, but the impulse should not trigger a node, is that not a downside of dot product? Yes, that's the downside of dot product, and that's why we have the activation. What activation really does is those huge output of all that of all that of the dot product is been mapped to 0 and 1, right? We are we understand analog values. If we provide the threshold of 0 and 1, the hard threshold of 0 and 1, that's linear in nature, that won't capture complex features, and that's not very helpful. So we require analog values, a continuous range of values between a range. But that range should not be very high because that would be hard for computation. Thus, if we map those dot products to some other range using some function known as activation function, in case of sigmod that's 0 and 1, right? In case of tan h that's -1 and 1. That mapping is reducing the high impulse. Changing the activation function is something like the bandpass filter. Bandpass filter, you can say, but activation, all activation is doing is mapping those high impulses into a smaller range. Good for computation. Yes, DSP concepts are very nice for analogies, and since this mathematical modeling, which was my aim to give a peekaboo of what the analogy of an artificial neuron to a biological neuron is. I hope somewhere or the other I try to make that clear. If there are any questions, I'm up for that. Actually, there are many things that cannot be covered in an hour session. There are many technical details that we can go into, which will take time, and eventually we'll cover all of that. I guess no one have any question right now, so I guess we should end the session. So thank you everyone. You can connect me on LinkedIn, and for any query, you can either mail me or we can have the discussion on the Slack channel or WhatsApp. So